Hello. Let's look at another problem in introductory dynamics. Again, I'm collecting some problems that I think are more valuable, and I'm trying to, at the end of the day, in a few months, I guess, I'm going to collect like 40 or 50 problems and create a workbook from those problems. So these are the videos I'm creating, and as I create them, I upload them on YouTube. If you have questions, my email is available on my about page, and then you can also connect with me through LinkedIn. All right. So the problem we're looking at today is again, it's almost lesson. You could think of lesson one. It's from point mass kinematics. So we have the motion of a high-speed train is characterized by velocity time graph, and compute the displacement time and acceleration time diagrams if the displacement is zero at time equal to zero. So we always need to have displacement at time equal to zero, right? Because if you look at this diagram, we have this information, for example, from the diagram that the velocity at time equal to zero is equal to zero, but we don't know if displacement at time equal to zero is equal to zero. How do we answer this question? This is pretty straightforward, meaning that it is essentially one of the calculus-based physics questions, and it's not really complicated. It is pretty straightforward because it's mostly math. So although it is about velocity versus time, all we need to know is, all right, how we define velocity and how we define and compute acceleration. We know that velocity is ds dt, s being our location or displacement. And we also know that our acceleration is dv dt. If we differentiate our velocity, we get our acceleration. In fact, acceleration is pretty straightforward to compute because all we need to do is to differentiate our curve at any point. Now, if you pay attention, here we have essentially three segments, and we need to divide our motion to these three motions. We have a segment of the motion initially that the velocity increases. So the velocity increases from 0 to 20 meters per second in 10 seconds. And the velocity then stays constant, and the velocity starts to increase again from 20 meters per second to 60 meters per second. All right, so first thing is to compute velocity. We know that we differentiate displacement. So we simply can integrate this expression, rearrange the terms, and have ds equal v times dt, t being time again, and s being displacement or position of this point mass. Differentiate velocity. All right, so let's look at the segment between time 0 and time 10 seconds. This is a straight line, so you can immediately see that the velocity is essentially 2 times displacement, or 2 times the position of your mass, your high-speed train, because this is a straight line with a constant slope. All you need to do is to divide 20 by 10 and get to as the slope. So you know that this v between 0 and 10 seconds is 2 times t, 2t, integrate that, you get t squared. So at time equals to 10, s is equal to 100 meters. Again, so once we get to this point, you understand that it becomes 100 because the initial condition was equal to 0. So for example, if I had said the s at time is equal to 0 is equal to, for example, 5 meters, what would have you said the s would be at time equals to 10? You would have said, all right, 10 squared plus s equal to 5, is 105 meters, the current position at 10 equal to 10 seconds, right? All right, and then we have between 10 and 20 seconds. Between 10 and 20 seconds, your velocity is constant, 20 dt, all right? So, and then you integrate from t0 to t. In this case, our t0 is 10, because the velocity for this segment of motion is constant between t equal 10 seconds and t equal to 20 seconds. So 20 dt, so I get 20 times minus s0. All right, so, but where does this minus s0 come from? If you, first off, this t itself, it varies from t0 to t, all right? So t0 is 10, t is 20, so this term is going to be 20 multiplying 20 minus 10 multiplying 20, right? Which is 20 by 10, which is 200, right? And then I apologize, this should be a plus. And then we have s minus s0 from the left hand side, and I'm moving s0 to the other side, right? And s0 was 100 meters, so 100 is added to 200 and gives me 300. Agreed? All right, if it's easier for you, if it is confusing, what you can do is write it this way: t0 to t plus s0. This should be pretty straightforward and pretty easy to understand. Integrate the right hand side to get 20t, and t varies between t0 and your current time, between 10 and 20, and you multiply that by 20, it gives you 200, and plus s0, which is 100, it gives you 300. Right? Now let's look at third section, or the third segment, or the last segment of motion, t between 20 and 30. The first thing we need to do before being able to use equation 1 is to describe velocity. How do we describe velocity between 20 seconds and 30 seconds? Again, it's a straight line. So from basic algebra in high school or in university, you know that the equation of this line is going to be 4 times time minus 60. Right? This is a straight line with a slope equal to, how do we compute the slope of a straight line? The slope of this line is 60 minus 20, which is 40, over 30 minus 20, which is 10. So 40 over 10 gives you 4. So the slope of the line is 4t minus 60. Right? If you wanted to test, okay, one more thing here. Once you have your equation of the line, just do a quick test and make sure you do have the equation right. Meaning that if I insert t equal 20 into this equation, I get 4 multiplying 20, 80, minus 60, 20 meters per second. If I insert t equal to 30 into this equation, I get 4 multiplying 30, which is 120, minus 60, 60 meters per second. So always test that. Then you substitute 3 into 1, and you get s for your current time, which is 30 seconds. Again, same thing. You integrate, you substitute, and you have your S0 in this case being equal to 300. Where does the 300 come from? 300 it is your position at time equal to 20, which is essentially the T0 for this segment of motion, right? So I could remove these two segments, and I tell you S as time equal to t equal to 20 seconds is equal to 300. And these are the numbers you have. And you should be able to get the same numbers for S. So you simply, again, you substitute t equal to 30 seconds into this equation, and you find S as equal to t equal to 30 seconds. So this was our ST diagram. And now we can draw this ST diagram. And for AT, or acceleration time diagram, you have a very easy life, because AT, acceleration time, is simply you differentiate the velocity during each segment. So all you need to do is between time 0 and 10, you need to compute dv dt, which is the slope of this line. And this line goes through the origin. You know from basic algebra, for example, that the slope of a line going through the origin is simply 20 over 10. So you simply divide the y by x and you get the slope of the line. Between 10 and 20 seconds, the velocity is constant. When the velocity is constant, you could quickly answer this question that it means that the acceleration is equal to 0. And between 20 seconds and 30 seconds, the acceleration is again the slope of this line. And what is the slope of this line? The slope of this line, we have already calculated that, and it was 4, right? And how did we compute the acceleration or the slope of this line? We said that, you know it from basic algebra again, 60 minus 20 over 30 minus 20. So which is 4. So all we needed to do in this calculus-based mechanics problem was to use some math, integrate properly, and differentiate properly to compute ST and acceleration time diagrams. So all we need to pay attention is two things: integrate/differentiate correctly, and also substitute initial condition for each segment correctly. Thanks for paying attention to this section. Send me your questions. My email is on the about page. Connect me on LinkedIn, and I'm going to see you again for problem number 4, Introductory Dynamics.